Carrying on with the lectures on basic data science modules, we'll pick up the discussion of NumPy arrays. So we have some understanding of this new array data structure, and we saw that we can construct an array by calling numpy.array on a list of lists, or even a list of lists of lists. The hierarchy could go as deep as we want, depending on how many dimensions we want in our array. Often, we will want to generate an array not necessarily from some particular collection of manually entered data, but rather from a specific state. For example, we might know we want an array of a certain size where every element is 1 or every element is 0. Or we might want an array where each element is between 0 and 1, evenly spaced, and we want 100 such elements. So these are pretty common cases. For example, if we want to make some kind of graph, we might want linearly spaced points on our graph between 0 and 5, and to get good resolution, we'll have 1,000 points along that axis. So that's kind of a use case we'll see once we start talking about plotting and visualizing data. NumPy provides a number of convenience functions for generating arrays of particular forms. One example is what I've just been describing, linspace. So we can get linearly spaced points between some starting number and ending number, and we will get as many points as we ask for. So if I want 5 evenly spaced numbers between 1 and 10, I get that. 1, 3.25, 5.5, 7.75, 10. This might be a little bit different than you would have expected, knowing that, for instance, 10 and 5, 10 is evenly divisible by 5. But if we were to have 0 here, actually, even if we had 0 here, it would be a little bit different than you would expect. So knowing that, there's 10, that 10 is evenly divisible by 5, you might expect 0, 2, 4, 6, 8, 10. But if you count up the numbers I just said, you'd discover there are 6 numbers. Because linspace is inclusive of the upper bound, we do have to be a little bit careful about if we want particular values here. Linspace may not be the best choice. In that case, we may want something like a range, which is just like the built-in range function in Python, except instead of returning a range, it returns an array constructed from that range. So this is equivalent to if I had done np.array range 110, and I would have gotten the same result. So 2 different options for getting numbers that increment steadily between 2 bounds. In one, I select my lower and upper bound and then my step size. In this one, I select my lower and upper bound and how many steps I would like to take. So these kind of complement each other. We can also have logarithmically spaced points. So from 1 to 10, if we wanted 10 logarithmically spaced points, So this is actually my mistake. I misspoke. This is not going up to 10, but 10 to the 10th power. So these are powers of 10. And I'll take even steps in powers of 10 or the natural log, a number. I don't remember exactly which. I believe this is powers of 10. NumPy log space. So we can specify what base we want for our logarithmically spaced points, and by default it is 10. I mentioned in a previous lecture, I'm often going to be looking at documentation for various functions because I don't quite remember how they work. This is very realistic. I've been using Python for many years, but I still don't remember how everything works because there's simply too much to remember. So this is maybe the first example in a while where, because I haven't known something, I've had to look up the documentation. I suggest that you develop the habit and practice finding information in documentation as I just did, because just like me, you too will not be able to remember everything. So if you needed to know, for example, are these numbers base 10 or base E, you might want to Google that NumPy log space just like I did, and then come to the documentation and see, we can choose what base we want, but by default it's base 10. And it also describes the other thing I forgot, which is not that it doesn't start and stop at the numbers you give, but it starts at base raised to the start number, and it stops at base raised to the stop number. But in any case, we can also get logarithmically spaced points. This can be very useful. I mentioned earlier we might want arrays that are populated entirely with zeros or ones. We can do that. So far I've been showing one-dimensional arrays, but we can also get multiple dimensions. Whoops. So here's a 10 by 5 array of zeros. You can even have 3 dimensions. So here we have 10 sort of stacks or slices of a 5 by 2 each. So 10 by 5 by 2 array of zeros. I'm actually going to change this to 2 by 10 by 5. So we have a 10 by 5 structure we saw before with a depth of 2. We can construct diagonal arrays. So if you're familiar with the term diagonal matrix, a matrix which only has entries on the diagonal, we can easily construct those with NumPy. Or the identity matrix using this I function. So the identity matrix is a diagonal matrix with ones on the diagonal. And we say how, and the identity matrix is always square in shape as well. In fact, a diagonal matrix must also be square in shape. And we say how many elements we want along the diagonal. As you might guess, I've mentioned the word matrix a few times. If you're familiar with linear algebra, NumPy is often used for doing linear algebra. We'll discuss this in the subsequent lectures about NumPy. We won't be using its linear algebra features that often ourselves in this course, but it is one of the more common uses of NumPy. We can also, this is sort of an aside, not connected to the things we've been discussing, but if we want to change the type, the data type of an array after it's created, just like we could cast an integer into a float, or a float into an integer, we can recast the data type of a NumPy array, and as long as it's unambiguous how to perform that coercion, then NumPy will go ahead and do that for us. So this log space array has a data type of float, but it so happens that we have 10 raised to various powers here, so we might want to instead cast that as an integer for our purposes. So by using the as type method of an array, we can recast that array to a different data type. Now, we can't do this for every kind of array, but as I mentioned in the previous video, almost always with NumPy arrays, we'll be working with integers, floats, or Boolean values. And there are clear-cut, unambiguous ways to coerce those different data types into each other. 0 can be coerced into a Boolean as false. Any non-zero number would be true. To go from a float to an integer, we simply round or truncate the floating point number. To go from an integer to a float, we simply add a decimal point to the end of the integer. If we want to go from Boolean values to floats, we can also do that, where true will be coerced into a numerical 1, and false will be coerced into 0. So I'm going to conclude this video here. We've now had 2 videos discussing arrays, both their structure and how to create some useful quick arrays following certain formats, certain common formats we might need at various times. But so far I haven't really motivated very much why NumPy is useful. I mentioned that it's highly optimized for performing mathematical calculations, but I haven't explained that yet. In the next video, we'll motivate why NumPy is so useful.